Moses? Luke?
Hello.
All things?
Pretty good.
Give me a second. Let me. Come on. Go down. That's good attendance. We have 4 people on time. Lately.
I just realized my hair is
Huh?
messed up.
Tell it again?
I just realized my hair is messed up.
Ah, that's okay.
I'm still.
Being on camera,
Looks like.
otherwise you would have done realized and you would have been very
Looks
happy.
like there is a bundle of hair which is pointing up. Here.
You and me both, Avinash.
Yes, Luke.
Towards your right.
Okay. How was the? Did everyone submit, or are you guys still working on that?
I was just doing that last detail for that
Oh,
order.
yeah, sure. Oh, yeah, yeah. Oh, yes, I should ask, what does this mean? What does? What does this mean?
It means we are
Is that-
neglecting the order of x squared.
Okay, so is that a standard thing? Do you guys see other places? Where do you see?
I've seen that in your classes. I've seen that in Dr. Mazumdar's class.
Other than me and Dr. Mazumdar.
I did not see that anywhere else.
Luke, are you familiar with this notation?
Yeah, I don't know where. I've just seen it.
Yeah, I'm wondering if this is a Indian notation by any chance. Because I have heard this before also, they're not familiar with this, and I'm wondering if there is a cultural thing involved in here. So do you remember where you saw it? Have you seen it in a book, let's say?
In a book. Maybe not in a book, but I've seen it a lot in classes.
Okay.
I saw it in the textbook.
You saw it in the
I
textbook?
actually saw it used in the textbook.
Oh, okay, so then I'm good.
They did a solution to something and they put that.
In our image
I think it was on the
fingers.
textbook, yeah.
Oh, okay, so then I'm good.
I think they use like
12 pages.
Oh, wow.
I think they use like curly O's.
Yeah, it's supposed to be. I mean, when you typograph it, this is supposed to be. That's just it. But it's.
It's based on the old cursive O that nobody knows how to write.
Yeah. There was the calligraphy class in my I don't even know when was it, elementary school. Yeah, I never went to that class. I had a terrible handwriting.
Leah? Hello, Moses?
I did that in art class.
It is a different
Morning.
background.
That's a new background he got downloaded from the internet.
No, it is not a downloaded.
You're talking to me.
It is a
I'm
real-
I'm at my mom's. I'm at my mom's house. So
I was kidding,
What
yeah.
is that on the wall?
Yeah.
It looks like So,
You get too curious.
hey, Moses, what is the thing on your wall on the left, on your left side? Yeah, is that like a temple or something?
The cloth?
No, no, the other side. Is that the left side or is that the right side?
What are you pointing at?
Oh, that thing.
The red star or the
There's a thing
on
that
the
looks.
shelf? I don't know what you're pointing at.
We just got them hiding over.
Yeah, you'll have to come over sometime.
There are three things, right?
On the
There are
shelf?
three. One is a red star, one looks like a clock, and the other one?
Well, there's a box of stuff. There's a kind of a shelf on the wall. It actually is a shelf. There's a golden T-Rex up at the top. I don't know if,
The one below that?
and below that on the, I don't know if you're pointing to this stuff, but there's
Yeah, I'm pointing at that.
a little box with stuff. This is an elephant. Yeah, actually that's like it's a triceratops or something anyway.
Okay.
Yeah, you'll have to come over sometime. That's
Well, Moses, thank you for the tool.
wait, what did you say?
Yeah, I'm just curious whenever I see a new background.
Yeah, for sure.
Good.
Congratulations, Michael.
Thank you.
So
It was
Michael,
really good.
Yeah, a fun weekend.
Yeah, it turned out really, really good.
Mm.
And
That's awesome.
got
Beautiful.
it.
Awesome, man. Wow. Well, congrats.
Thank you. Thank
Yeah.
you.
Yeah.
Okay. Okay, how was the submission? Or did you guys finish the exam? Actually, there is more time, right? So I shouldn't. How is it going?
I have not quite finished it yet, but I think it's going
But is
fine.
it going okay?
Yeah.
Seems reasonable. Okay.
I think so.
Was number 6 too unreasonable?
That step that we went over in class, solving for the constants, just getting to that point. I mean, it wasn't unreasonable, but it was difficult. I mean, I don't know that I would have quite gotten it on my own.
Okay. Maybe. Yeah. Yeah, seems to me. What do you say, Rob?
Up until the putting it into the Laplacian, and then just the steps, the extra steps put in there helped to really see that.
Okay.
And it made a lot more sense.
Maybe I should put it in the end, now that we have gone through all this, was it useful? Because that's the new thing you're learning. Would you say it was useful?
I would definitely say it's useful, yeah.
Okay, yeah. So if not, like, go over it. This is the new thing we are learning, is that orthogonal function, how to use orthogonal functions in practical moments. Or the idea of function spaces, if you will. Okay. We introduced the idea of electric polarization last time. We want to do some examples today. I'll start with some elementary example and one elementary example and one reasonable example which gives a better picture of the whole thing. How do you move this? Okay. So we'll call this examples on electric polarization. Okay, so what we said, what we derived I think it was about a week ago or something, right? Was it a week or maybe more? Seems like already this class meets after 5 days. I forget what is going on.
Yeah,
And I think last time we missed.
Yeah, I think any class should be on Monday, Wednesday, Friday.
Monday, Wednesday, Friday.
Yeah, I think major classes should be on Monday, Wednesday, Friday.
Usually the complaint is
They
that,
should be like spread out a little bit.
yeah.
So it's not like a lot of information on the same day and you don't meet in like 4 days.
Yeah. I get your point, but usually the instructors complain the opposite. When it's a graduate level class, it is not easy to cover stuff in 50 minutes. So you begin something and you're not able to finish, and then next day you have to come back and restart the whole thing. I think that's why graduate level classes usually they make it 7 instead of 50. But I understand your point, like what's going on in this class. It's little, at least for me, it is. But then you guys read these things more than me. I only do it on Monday and Friday, probably. Hopefully, you guys do this more often. Okay, so let's write out the Maxwell's equations, right? For macroscopic Maxwell's equations. So that's divergence of the displacement field, if you want. So that's R and R and yeah. So let me keep it as it is. Right? That's equal to rho of R. And that is del cross E is equal to 0. There is a slight issue in this, the way we have written it. It's of course electrostatics because we have neglected this. But at the same time, as we will see in the next class, it's not purely electrostatics because we are talking about D having an influence from, so let's say, so some influence if there is a time. This is epsilon of R times the electric field of R, right? Isn't this not what we did? Actually, let's make it better. Sorry. Because in what we are going to do today, it's like easier if I just not talk about it. Okay, so this is better. So this is what our Maxwell's equation looked like if there were charges and what are the fields generated from there. But if there is a material, we said overall the material acts as if there is an additional charge. And that is given by a polarization density. So what is P now? So this is P is a function of R, where P of R is nothing but dipole moment per unit volume. So that's the simple idea. The material is neutral, so no charges, so the next higher contribution comes from the dipole moment. So if we are given this P, and let us for in the examples we will do today, we will say that there are no free charges. If we are given P, take the divergence of that from that point on, it is basically just the idea of charges itself. But it's good to have an idea of what kind of charges or what kind of charge density does come about. So example is, let's say we have a slab, right? Can take, I think in, I don't know, I forgot your homework. Either you can do parallel plates or you can do half slabs. So let me do the half slab. There's a good chance that if you have one. So another example is, this is another example. So there is a material of having a planar material of width d, and this goes to infinity in this direction. Those are the 3 dots mean they go to infinity, right? And this is vacuum. This is vacuum, and this is a material. How do you define the material? We have to give the charge density for this. I'll let you guys do this example, especially if there is an exam or something. That's a good example to work out. Like that's an easy extension in principle, if it's not already in the homework. Okay, so what is P for this? So we're talking about dipole moment per unit volume. Let's say it is uniform inside the material, and it is there only on one side, right? So let's say this is z equal to 0. That's your z equal to 0 plane. So that means step function, correct? So step function, and it survives if z is less than 0. So that's z minus. So if 0 is greater than z, then it, so it has a direction now. So we have to give there is a dipole moment at every per unit volume, and we can choose a direction associated with it. And let us say it is in the z direction. So extra credit. And this is another problem I asked in the exam, or at least in the past I have asked in the exam, is what if this was x hat? So what is the repeat the whole problem for x hat? And the answer is supposed to be, if you just look at it, even without a calculation, sometimes you can get the answer. So try to interpret this, what is going on. As we proceed, it might be clearer. If we have to put some uniform polarization density, how much dipoles per unit volume? Let's say that's sigma. Okay, what does this mean? Let me make it a little more clearer. This means there are dipoles, right? So this is positive, negative dipoles, negative, positive dipoles. So that's how it looks like, right? So there are lots of dipoles, and they're all aligned. It's like a magnet, right? Electric version of the magnet. And we would like to know what is the electric field due to this, or what is the electric nature of the surroundings because of this. And what we are told is that instead of doing this, just take the divergence of this, and that acts like a charge density. So let's calculate that. So rho effective is equal to negative divergence of P, and that's equal to negative divergence of this whole quantity in there, right? So there's sigma, which is a constant, does not depend on the position, and we have a step function. Okay. This is a constant, can come out of the gradient. Z hat does not depend on the gradient. Those quantities come out. I can write this as minus sigma. Z hat has to dot with this. That's the only quantity it's dotting with. Z hat minus Z. Gradient in the direction of Z hat is derivative with respect to Z. That's minus sigma derivative with respect to Z of minus Z, right? Because only that component survives for the gradient. This is also sometimes called a directional gradient when you dot it with a constant vector. It's called a directional Oh, great. Okay, so what is this? Equal to derivative of a step function, delta function, and the negative signs that cancels that out. Pretty good. So this is sigma times a delta function. And we know what that looks like, right? So now if I were to interpret this, there is a charge just on a line, correct? There is a surface charge. So this whole problem is equivalent to, forget this and just have a line charge which is only at one point. So that's all positive charges and nothing else, like this is zero. So the electric or the electric nature of a uniformly charged plane is equivalent to a material having a uniform dipole density inside, right? So that's the physics associated with it. And one can interpret, even though it is not obvious at all, that these positive negative cancel, this positive negative cancel. So there's one left out. But why not do that? I mean, so it's not at all obvious.
So what happens to the negative charge that's all the way in the left?
That is correct. So that is the source. Remember, there will be an electric field now. So there will be electric field ending here. It has to originate from somewhere. So that's from the infinity. Like it's like saying if you have uniform electric field, E. Correct. Electric field always has to originate from positive charges and end in a negative charge. So my understanding is that at infinity you have a lot of positive charges, and at positive infinity you have a lot of negative charges. But we never talk about it because infinity is not part of our system. If you want, does that answer it?
Yeah. And then I guess my follow-up question would be: would the electric field be going out of positive outside of the material and then curving around to go to negative, or could it just go inside of the material?
This is infinite, right? So it never ends, right? So it cannot come back. Like it is uniform. Once whatever is there here has to be here, just because of translation symmetry. Your question is, oh, can you come back like this? No. Physically, that's not possible. That doesn't happen. If it was a capacitor, yes, if it was a finite capacitor, that is positive, negative. If this ends, there's a difference. Right? Then you can say that, oh yeah, I can do this. But if this never ends, this goes all the way, you can never do that. Is that clear? Is that your question?
So does that mean the electric field would be towards the left?
Yes, that should be something to the left also, right? That's what we would expect. But it's, let's see what it is, right? So we are saying that, oh, inside of the material, there's an electric field. So what does that mean, right? So we got to interpret that. Let's come back to that. Yes, the answer to your question is yes, there will be, because this is what we understand, right? For a positive charge, there will be charge this way, electric field this way, and that way. But then what do we mean by an electric field inside of the material? So let's hold on to that thought. The main point is that you have to subtract. So if you take this onto the left-hand side, this can subtract that, so there is some cancellations there. So inside a material, you don't talk about electric field. You talk about the displacement vector, D. That's what you talk about. So that's the idea. So we'll come to that a few minutes later. Okay. So that's what it is. Have we done the electric field due to a planar charge in this class before?
I don't think so.
I don't think so. So, okay, so we have to do this, right? Okay. So maybe this will get extended with another class. So, okay, so that's fine. So this is practically speaking reasonably. This is even done at an undergraduate course or even introductory level physics course. But let's do this again, right? Why not? So electric potential, you do. Maybe I should ask you guys before that. What is the electric field due to a positive charge, which is a planar positive charge, an infinite basically a plane of infinite extent with uniform charge on it.
Well, it's constant and isn't
Sigma
it?
over 2 epsilon naught.
Very good. So it's a constant, right? Yeah, sigma over 2 epsilon naught. Very good, right? And what is the electric potential?
Mm,
It's a constant, correct?
mm. Okay.
So remember, electric field is negative. Yeah.
If you integrate the electric field, do you get the potential?
Yeah. So negative E dot d. So what is the electric potential? Derivative of what gives you a constant?
It would be a linear,
Linear.
Linear thing.
Linear, right? That's what you would expect. Moses, is that what you're saying?
Yeah.
Yeah. Okay. So you expect it to be linear, correct? So the potential should be. Does the electric field go from high potential to low potential, or from low potential to high potential? Yes. So this is higher potential. That's a lower potential. So that's higher. So the expectation is that somehow this is higher potential, and then it goes lower. So if you were to plot this, maybe, right? Maybe if this is your Z, this should go like this. Maybe if it is 0, right, on the pipe. And what about this side? Right? So on positive Z, it is this way, right? Because it is linear, but then it has to decrease, so there was only one choice, right? You can start from a constant if you want electric potential to be a constant. What about that side? Right? This side?
Reflected analysis.
Yeah. What's on this side?
I just said you just reflect the curve.
Reflect, right? So that should be better. Right? So that should be much better than the other way. So, so we should get this. So that should be the answer. But it'll turn out that that's going to be a challenge. Okay. The issue would be that electric potentials are off by a constant, and we will see that in this case, the constant is an infinite constant. So it is not very easy to derive this. So we'll try to do some limiting cases and at least capture that electric potential. So let's see. That's a good exercise to do that. Electric potential using superposition principle is 4 pi epsilon naught EQ r prime times rho of r prime over r minus r prime. And in this case, it's just effective, right? There is only one charge, so it's an effective charge in there. And in math methods, we also showed that this is actually the Green's function, right? 1 over r minus r prime is the Green's function associated with which equation? It's called maybe I didn't clarify this better. What is this equation called? What's a differential equation? What is this called?
It looks like Helmholtz equation to me.
No.
No? Not
at all. It's called the Laplacian. Helmholtz equation is a wave equation when you have the time also in it. And if you have a source associated with that, that's equal to rho, that's called a Poisson equation. Okay. So that's just nomenclature. We have been using this all through. It's just most of electrostatics deals with solving the Poisson equation. And the Green's function associated with the Poisson equation is 1 over r minus r prime. So So this is a Poisson-Green's function if you want. I don't typically call it like that, but that will be a technically correct statement. Okay, so we want to calculate the electric potential everywhere at an arbitrary point here. Let's say, so we just substitute. So this is 4 pi epsilon naught. So this is dx prime, dy prime, dz prime, all going from minus infinity to plus infinity. This should be an easier problem after the more complicated problems you have done. This is sigma delta of z prime divided by the distance between a source point here, and this is x, y, z, and this could be x prime, y prime, z prime. I show it down there because it survives only at that point, right? Because of the delta function. The distance between them will be x minus x prime square plus y minus y prime square plus z minus z prime square. I have to take the derivative with respect, sorry, integration with z prime is immediate, and that's equal to and I will also do one more step right away. I can substitute x prime minus x to be x double prime, right? And y prime minus y to be y double prime. Right. And why I do that is basically, notice that if I move this along this direction, nothing changes. The electric field here is expected to be the same as the electric field here because of symmetry. And that means to say that it should not depend on x and y. That means you can get rid of it, and that's done by the substitution. So do that. So there's sigma over 4 pi epsilon naught. I bring it outside. Dx prime is dx double prime, and the limits remain the same. So that's dx double prime, dy double prime minus infinity to plus infinity. And this becomes z prime goes to 0, and x minus x prime is x double prime square plus y double prime square plus z square. Sorry, yeah, square, right? Yeah, that's good. I think so. Okay. And that should be a straightforward integral, correct? Okay. So phi apparently does not depend on x and y. It only depends on z. Right? That's a realization now. I can write phi of z now. This is equal to sigma over 4 pi epsilon naught. There are two integrals, x prime and y prime. It's good to, this is an integral on a plane, right? We use cylindrical coordinates, cylindrical polar coordinates in 2 dimensions. So I can change that integral to 0 to infinity, rho double prime, and 0 to 2 pi e phi double prime. That should be clear to you guys. And that's rho double prime square plus z square. Right? That's the only quantity that it depends on. In this way of writing, it's very clear that it doesn't depend on the angle. It should not, because it's a planar uniformly charged plane. So this is 2 pi. I can bring that out. And 2 pi, so this is equal to 2 pi. 2 pi cancels that. So this is sigma over 2 epsilon naught. Ravinat was saying that electric field has to be that. So this seems to be the electric field here. And if our understanding was correct, that should be, this integral should be x or z actually, right? So that's 0 to infinity, rho double prime, and then rho double prime square plus v square. Okay. What's the substitution for that?
I think you can just simply use a U substitution.
U substitution, what is that? Tell me.
Like substitute U is equal to rho double prime square plus V square.
U is equal to rho double prime.
I think you could also do with tan substitution, but it's unnecessarily hard.
Let's do this. Well, this is simple. Right? But there's a challenge, right? Why not U square? Shall I do U square? U is also perfectly fine, so U square. So this is 2 times U du is equal to rho prime 2 rho prime E. Correct? And that's equal to sigma over 2 epsilon naught. Then rho double prime is 0. U square is Z square. So U is equal to magnitude of Z. The magnitude of Z coming. And what is it when rho is infinity? Right? U is infinity, right? So that's U du and divided by U square square root U, that's 0, and sigma over 2 epsilon naught. And what is that? What is that? Integral equal to?
Like it diverges.
Sorry, it diverges. Right? It diverges. So it's not nice, right? And you cannot do much about it. Something diverges, it diverges. Etc. But you do notice that if I were to write this, right, something like this is infinity. This is meaningless what I'm writing, right? But you do see the minus delta z, magnitude of z. Right? That was your plot, right? If I were to plot this minus magnitude of z, that's this. Right? So derivative of this does give you the electric field. But what is this infinity? Like this is meaningless whenever you subtract. Right? So you want to comment?
Oh, I was just going to say, if you want to calculate the electric field from that equation, looks like you still get electric field.
Yes, you will get the electric field. That's why I think it is good, but it is very discomforting when you have something. There's an infinity. You don't know what mistake you're making. So let's make this a little more, slightly better. At least be confident that this is what is happening. It will still be divergent, but as not as bluntly as this is, right? This is really infinity. So let's do this slightly better. So let's go back to our plate, and let's say that the plate is actually not infinite. Let's say it is finite. Right? So we don't say it is an infinite plate. So we say it's a finite plate, and it is let's say a disk of radius r. It's a disk of radius r, but we want to keep that limit r. So most of this first few steps will go through.
Can we do this like we say it's a radius r and then take a limiting condition?
Limit r tends to infinity. Yes, exactly. So we will give some structure to this infinity. That's all we're going to say. We just want to make sure that there is no z inside this. Like, because if there is a z inside this, then the derivative will catch that. Then the electric field will have that infinity. So we just want to make sure of that. And it is not at all obvious here that is there some z dependence in there? We don't know. Right. So let's look into that. So we say instead of doing a finite case, let's say that this is a disk of radius r in the limit r tends to infinity. You're not doing the finite disk. Most of the steps go through, except here, right? This will become capital R now. So it's a capital R, and we are saying limit r tends to infinity. So that becomes a limit r tends to infinity. That's r, and rest everything remains the same. I'm actually erasing stuff and doing it for you guys. If you're writing with, not writing with an eraser, it might be hard. If you're not writing with a pencil, it might be hard. So that's your r. This gets limit r tends to infinity, and it goes through here, right? So you get r. Oh, that's not r now, right? That's not r. But this is rho prime. Rho double prime goes to r, but this one now goes to r square plus z square. That's your limit. So this is r square plus z square. That's fine. And notice this infinity that we said was infinity was actually not infinity. It had z dependence in it. Right? There is a z dependence in it. Actually, you do see this in your problem 6 of your exam. Right? We evaluate the field due to a disk. Right? If you go very close to the disk, right? If this is your disk of radius r. If you go very close to it, that's pretty much infinite disk. So you should get the electric potential like that of a disk very close to that. And in the end, in the last part of it, that's what you're doing. You drop extra orders and try to capture this answer in there. And that's pretty much what we will do here. So notice that again, what we said was infinity earlier is not really infinity, or it's not a constant. It does depend on the z. So how does it depend? R is very large, so I can take that common. So remember, this is limit r tends to infinity. So limit r tends to infinity of sigma over 2 epsilon naught, and I can take r out, and I have 1 plus z over r square. Which can be written as limit r tends to infinity. Now we actually take the limit. So notice this is our order. So this is r minus magnitude of z plus order. This is calligraphic order, right? What this means is that I'm neglecting a lot of things of order z over r square and higher. Anything beyond that, that's okay, because in the limit r tends to infinity, all of them will be small. But the first term is not. So that's infinity still. And this was the infinity we missed. So here, when we look at it, it seems like, oh, that's a z-dependent quantity. But in the limit r tends to infinity, all of them are small, but you still know what kind of divergence this is. This is a divergence associated with the plate being very large. In practice, typically we don't deal with that big plates, so this is not expected to be there. Or at least it will be there, but it will be a constant. Okay, so that's your electric potential. What about electric field? Right, so let's use the electric field now. Electric field is negative gradient of the electric potential. That's negative gradient of this whole quantity. R is a constant. There's only z that survives. Right? That's so sigma over 2 epsilon naught, and limit r tends to infinity. R minus magnitude of Z. The first term, you can take it, typically how you can argue this, but it doesn't help much, is that take the limit afterwards. Right? First take the derivative that kills that R, and then take the limit. So this is the same as pos actually, limit R tends to infinity of sigma over 2 epsilon naught and gradient of magnitude of Z. So you take so now there is no need to take the limit. So that's equal to sigma over 2 epsilon naught. And what is gradient of magnitude of Z?
It says Z hat, but I don't know
So
how to
that's
do
Z
it.
hat times derivative with respect to magnitude of Z.
So it's gonna be,
Yeah, what is this? So that's 1 and minus 1, right? It says greater than 0, it is 1, otherwise it's a minus 1. So that's the same as, you can say sigma over 2 epsilon naught, and it's plus Z hat if Z was greater than 0, and minus Z hat if Z is less than 0. And that answers your question in the beginning. What does this electric field look like? Right, so there's positive charges here. Positive charges here. And electric field looks like this. But this is material. There is a material inside. There's an electric field inside. Let's go back to our Maxwell's equation and interpret this as well. Our Maxwell equation was epsilon E. There is no charge, so it is minus divergence of the polarization vector. That can be written as with epsilon E electric field plus P is equal to 0, which is identified as P is equal to 0, and you define your D is equal to epsilon times the electric field plus the polarization vector. So let's see what this is. What is the polarization? So that's electric field. Polarization, what is a polarization? If you go back to the right in the first few steps, there was a polarization. It was like this. Right. It is P and a 0. Just to put in the numbers here, this is sigma over electric field is equal to plus Z hat sigma over 2 epsilon naught minus Z hat sigma over 2 epsilon naught. So this is for Z greater than 0, that's for Z less than 0. Polarization is equal to, for Z greater than 0, it is 0. It is plus Z hat, but this is just sigma now, right? Just sigma, right? There is nothing else, and just sigma. That's Z greater than 0, and that's Z less than 0. Let's see what is D equal to epsilon E plus P. So that's 0, right? So let's first write this down. D is equal to epsilon E plus P. We have to add these two quantities. So on the right hand side, the displacement vector is just the electric field itself. Outside of the material, there is no difference between the displacement vector and the electric field. But inside the material, they do some reconfiguration there. There is a sigma in the plus direction, minus sigma over 2 in the negative direction. So it is plus Z sigma over 2 epsilon. So that's Z greater than 0, Z less than 0. So if you were to plot your D now, something wrong, right? That is not epsilon. Okay. So D is equal to, it's the same. In fact, it is continuous actually. You don't even have to go here. Right? This is continuous. So it doesn't see the boundary at all. D is pretty much smoothly going. And what does that mean? D being continuous, you can see this as if you write, maybe I should do this slowly. Like if you do your Maxwell's equation, you have epsilon E plus P is equal to charge density. So material properties have been moved to the left. And this is equal to G is equal to rho. Let's take an interface. So since this came out to be so continuous, let's take an interface where on one side of the boundary you have one material and on the other side there is another material, or it could just be vacuum, right? So at an interface, let me draw a small volume, we call it a pillbox, Gaussian pillbox, and calculate the volume integral. That's dqr. And charges are not expected to be there right on the boundary. Whatever we talked about earlier, that was an induced charge, in the sense that was the charges from the polarization, not from this rho. Polarization is there inside. Right? Rho, maybe you can say it is very close to the plate, but then make your volume smaller than that. Like you have a choice in this volume. Make your volume so close that there are no free charges out there. So this will be always 0 inside that. I can always choose that plate to be so close to the boundary that's equal to 0. If that is the case, then I have, using divergence theorem, A dotted with D is equal to 0. Now what does that mean? I have, notice that I'm taking this to be very small. So this is supposed to be a very small thickness. There is an area on this side, area on that side. That's a volume, remember, that's like a pillbox. So this is a normal vector N1 times area, times the area A1 dotted with the displacement vector on the right, is equal, and there's one more, sorry, N2 times area 2 dotted with the displacement vector on the left. That's it, N2. And there are tiny areas here, but in the limit delta tends to 0, that goes to 0, so that's equal to 0. These two areas will be the same because when you really sandwich the two quantities, A1 cancels A2, so that's not there. And it is okay to say that N2 is actually minus N1. So you can write this as N hat dotted with D1 on one side is equal to and hat dotted with E2. And that's what we are seeing. Notice that the perp component of the displacement vector is continuous at an interface. This says that electric field is not continuous, it is the displacement vector that is continuous. This has some nice feature in this. Notice that if this was epsilon 1 times d1, let's say this is the parallel component, right? Parallel to the normal vector, that's equal to, electric field. And is equal to epsilon 2 times electric field. Parallel component of this. I mean parallel to the normal vector, not to the parallel to the plane, parallel to the normal vector. And this is nothing but your Snell's law, if you realize. Like, what it is saying is that there's a nice interpretation in here. You can inquire if you have an interface, and that's an infinite plane, and let's say this is epsilon 2 and this is epsilon 1, and let's say epsilon 1 is greater than epsilon 2, and let's say there is a charge somewhere here inside the material. There is an electric field that comes in. That could be electric field, right? And I would like to extend this to the right hand side. How do I know what is the electric field right on the other side? It doesn't have to be continuous, right? And the rule is this: if epsilon 1 is greater than epsilon 2, that means the parallel component of the electric field has to be less. So let's say this is, zoom this in. Right? That's your electric field onto the, that's your electric field right at the interface. And this is the parallel component. Right? Parallel is parallel to the normal, right? So that component has to decrease. So the next piece here, if I were to draw this box, so that's your vector. If it was continuous, this would have gone like this. Right? This is what I would have expected for it to go if there was no interface, but that's not what is happening. This has decreased a little. So this has decreased this length. This is your E1 parallel. This is your E2 parallel. Since epsilon 1, this is 2 and that's 1. Since epsilon 1 is larger, this has to be smaller. That means the vector has bent. Like a ray of light comes and bends, this is your Snell's law for the electric field. Why is this distance the same? This is your E1 perp, the component in the plane of the interface, and this is E2 perp. And E1 perp is actually equal to E2 perp. And why is that? So this is correct, this we derived. What about the perpendicular component? I'm saying it is the same. Why is that? What do you think is the source of that? From your earlier
Energy conservation?
energy? No. Maxwell's equation, look for the other Maxwell's equation, right? There's one more. Right? This is your divergence. That is a curl. Right? Curl of the electric field. There is no D notice. This is just E. Right? That's equal to 0. Again, you do this time not Greek divergence theorem. You do Stokes theorem. Right? This time it's a line integral. So you say this is dA on the surface, right? This is a surface now. dA dotted with curl is equal to 0. So you say this is line integral. Again wrong. dL dotted with E is equal to 0. And this again, if you do it around this, and this one I should give it as an extra credit. So extra credit, derive this. And do this seriously. Like, I know typically extra credit problems, I ask you, it is more exploratory in the sense mistakes are acceptable. These two, try, oh, this I already derived. This one, try to derive using Stokes' theorem. It's available everywhere. It's more undergraduate level. And that tells you that this is the same, but this length gets squeezed, right? And that's your Snell's law. Is that really what Snell's law is? What happens to a light ray that goes from, this is rarer and a denser medium, right? What happens to a light ray? When it goes from a rarer to a denser medium, what happens to the light ray? Bends towards the normal, right? The electric field bends away from the normal. What does that mean? Why is there a slight
Looks like E being larger means rarer.
No. Like, this is actually the optics. This is the source of Snell's law. Okay, Snell's law comes from this equation. But it seems like electric field bends away from I got the opposite result, right? How come, how do you, what is this, by the way? This is what? In optics, when you say that something comes and goes, what do you mean by that? What comes?
The propagation of the light wave?
Yeah, it is a propagation, direction of propagation. It has nothing to do with electric field, remember? Right? And in your, if you remember your, this is your K, right? And that's your electric field is perpendicular to that. And magnetic field is also perpendicular to that. This is the direction of K. Electric field is actually perpendicular to this. So right at the boundary, this is the electric field there. So again, let me zoom that in. So let me show that better. So the ray of light actually is bending towards the normal, but what does that do to the very good? So this is ray of light. So we do know that this bends, right? Now let's do the electric field. Electric field is perpendicular to this. So that's your electric field. Right? That's your E1 if you want. And right afterwards, it bends. Right? So that's your electric field after it has gone in. That's what is actually happening, but I showed it this way. So electric field in this way means that your ray of light is actually going this way, right? That's perpendicular to that. And this one, it bends slightly like that, right? So it does go. So notice if that's your electric field here, and it has to bend this way, so that's what it has bent. So that means your ray of light is this way. That means it has bent towards the normal. Right? Same thing here. If your electric field, this is your E1, that's your E2 actually, and that's your E1, that means it has to bend this way. Right? So it does go the other way. Okay. I wanted to do this for a sphere also, this whole analysis that we did for a slab. I wanted to do this for sphere, but I don't want to begin that now. So we will do that next time. So for a change, we can, I don't have anything else. Unless you guys, I don't mind. Stopping.
I was thinking we were missing somebody.
We are missing Jordan.
Yeah,
He did
Jordan.
inform me. He, like his grandmother got discharged from the hospital. So, and then she'll be put in the nursing home. So it's a very complicated scenario that once you enter the nursing home, apparently no one can go in or out. So she pretty much goes into a jail. So family wants to meet her before she goes. It's very hard. I mean, if you're an old person, like the only thing you cherish probably is the interaction with the family.
Is it because of COVID?
Yes. Oh, she was having COVID. I don't know whether you knew about that or not. Yeah, pretty bad. I don't know. It doesn't seem to be ending either. Seems like for all of your graduate school, you'll be just like this.
At least right now, we can still come to campus.
Yeah. I still am optimistic. I think this will all hopefully go away. But I thought when it was spring, I thought, oh, in August we'll be all over.
Isn't it supposed to be over on November the 4th?
Oh. Yeah, that'd be nice.
I don't know what. I mean,
It's a polarization. Yeah.
Oh no. It is just a conspiracy theory that Trump is saying. He's saying Democrats are only making this pandemic an issue because.
Okay, let's not go there. This will go. Let's stop the discussion.
No, it was supposed to be funny.
Actually, today we received the good news that my uncle is discharged from hospital.
Okay.
So I'd like to share with you guys. We talked about the other day. So he has been into hospital like for 6 weeks.
6 weeks.
He got an inflammation. Yeah, an inflammation in his lungs, and he made it through. So
yeah, you said he's relatively older too, right?
Yeah. He's I think he's 85 or something.
Wow.
So it was a kind of struggle for him. They put him in the IC. Yeah. So for a very long time. So he was on the ventilation. The ventilator, and actually today we received the good news from his son that he discharged from the hospital.
Good.
Yeah.
Are the cases how is it? Is it growing or decreasing, the numbers there?
Well, actually, they are like they still swinging. Sometimes increasing, sometimes decreasing, but it's they still can manage it. There are rumors that they could go back to the lockdown precautions that were in the beginning of the pandemic, but still rumors. There might something be in like mid-November or something, but everything, most of the cases here, most of the places here is under control.
Good.
And that's a good thing. Yeah.
So
also here the Minister of Health, they made I think it's a good step from the beginning of the pandemic. It was testing all the time. The more testing they do, the more cases they prevent,
Yes.
Yeah, that's what makes it under control most of the time.
Yeah.
And I hear it's getting very difficult there in US. Well, take care, guys. Please take care. It's very serious.
Carbondale seems to be managing better than it seems, or it's still recently increasing, but still it seems I would say in control.
Yeah, in Illinois, from the beginning of the pandemic, it's still way better than other places in US. I used to access the CDC website almost daily in those days, when I were in US, and I see numbers in some states are rocketing, getting up very fast. But in Illinois, they made it from the beginning, the precautions and lockdowns and those, social distancing and decreasing the number of people in the closed places. And that all of that helps from the beginning,
Mhm.
Yeah. No,
Yeah,
good.
I'm not sure what the situation is now. I know it's been increasing in the Southern Illinois area.
Yes.
Hasn't exactly been reflective in the number of cases that they're reporting on campus, which they only report weekly. But
our campus did what they did is that earlier they were reporting both the non-resident students and the resident students. And there was a significant factor of 10 difference. So they just stopped reporting the non-resident students.
that's what happened. They just stopped reporting it.
Yeah. So that's what brought it down significantly.
I would like, yeah, that makes sense.
They do have a link. It's not that I'm told by someone. They have a link in that same website, old data. And there, if you see that, it is just that they dropped the dominant piece there.
Yeah.
It is.
Are they still tracking that?
They must be tracking, but I don't think they reported. They just realized that it's like any other statistics. Give the best number instead of all the number.
Right. Yeah.
But Jackson is the right place to go. I think Jackson Health, what is it called? Jackson County Health Department, they give a reasonable statistics. Not statistics. They just give the number of cases and they maintain it reasonably well. So. But yeah, we can only watch those numbers. Not much we can do. Okay. Got on time. Let's finish on time today.
Okay, sounds good.
Take this opportunity to finish on time.
Yeah. Have a good weekend, guys.
Yeah. You too, Khalid. Yeah.
See you.
Thank you.
See you guys.
Bye, guys.
See.
Yeah.
Bye-bye.
Then you can see me wave.
Oh, I should have